Okay. So we are going to continue with our study of the kidney. So a recap of where we are. We know the gross anatomy, so the big anatomy of the kidney. We know that our functional unit of the kidney is the nephron. We know some of its parts. We know we have blood flow going into the nephron through an afferent arteriole, a glomerulus, then an efferent arteriole continuing into the peritubular capillaries. We know that we have filtration happening out of that glomerulus into Bowman's capsule or Bowman's space, and continuing into the proximal convoluted tubule, where we have a lot of reabsorption happening. And then we're going to see that fluid, that filtrate, continues on through the other parts of our nephron, through the loop of Henle, the distal convoluted tubule, the collecting duct, and eventually becomes urine after it exits the kidney, moves through the bladder, and out through the urethra. So last time we talked a bit about reabsorption and factors that influence our glomerular filtration rate. So we were talking first on Monday about filtration. We talked a bit about reabsorption, looked at the structure of some of the cells in the proximal tubule. We talked about the fact that sodium gradients and the sodium potassium pump drive a lot of this movement in the proximal tubule that we consider unregulated. It is active transport often of things that we want to recover like glucose, but we don't see an involvement here of hormones regulating what's crossing this membrane. And we talked about the idea of a transport maximum and how carrier proteins in membranes can be saturated or all filled up. So we can have spillover at certain concentrations of, for example, glucose in your blood, which would lead to glucose ending up excreted in your urine, which under normal conditions is not the case. So we ran through some examples of that. And I believe we ended about looking at this graph. Am I remembering correctly? Okay, cool. So that is a review of where we were. So we're going to pick up, finishing out with some of these processes and then starting to think more deeply about water, because a lot of what's going on in the kidney is regulation of blood volume, essentially. Okay. So reabsorption, that process we've been talking about, is return of filtered molecules to the blood. So in filtration, we have things come out of the plasma. Almost everything is coming out of the plasma. So the water in your plasma, the ions in your plasma, the glucose floating in your plasma, you're just keeping proteins, red blood cells are staying in your bloodstream. Okay, so that's all going into the nephron, all going into the kidney. So we need to reabsorb a bunch of that stuff because we don't want that all excreted as urine. So that reabsorption, you can see the arrow on there, is moving from the filtrate, from the nephron, back into the bloodstream. So they didn't show you the peritubular capillary that would be running alongside here, but that's where that blue arrow is going, into capillaries surrounding this structure. Okay, so it's super important because we are filtering a lot of plasma through the nephron, through the kidney. 180 liters of water is going through per day. You are only excreting 1 or 2 as urine, which is good because you do not have 180 liters of water in you at any given time. Okay. However, while your kidney is going to be able to regulate ultimately how much water is being reabsorbed and therefore how much blood volume you're maintaining, there is a certain amount of water that you are going to lose regardless, that you have to lose, because I don't want to be crude, but like you can't pee out like little chunks of salt, right? There needs to be some fluid for your waste products to be dissolved in. So there is a minimum amount of fluid loss that's going to happen. So that minimum is about 400 milliliters. So under all conditions, even if you really need that water, even if you're super dehydrated, you are still going to be losing some water in order to have something to leave those wastes dissolved in. So a minimum of 400 milliliters is going to be excreted in order to rid the body of all the waste products that you're trying to get out of the blood. Okay, so we consider that obligatory water loss, like you're obligated to lose that water. Okay. So most of your water, though, is getting reabsorbed. 85% of it is happening in the proximal tubules. We really try to reabsorb a ton of stuff really immediately as we're going through the nephron. So unregulated reabsorption, lots of it happening in the proximal tubules, which we consider our mass reabsorber. And then as we go into our loop of Henle, we're going to see that we have a fair amount of water reabsorption happening there as well. It's not until we get to the distal portions of the nephron that we have regulated reabsorption that's going to involve like hormone pathways. All right, so we're going to look specifically at water in that proximal tubule. So we talked about reabsorption in the proximal tubule from the perspective of glucose last time, but we're now tracking water because water reabsorption is really, really important. Okay. So you needed the glucose to make ATP to make energy. You need the water reabsorbed because you need to keep enough blood in your body, and your blood is mainly made up of water. Okay. Easily, or hopefully easy, water reabsorption is going to follow what's happening with your solutes, so the things that are dissolved, like your ions in the fluid. And this is basically happening kind of like through the process of osmosis, right? Like we know water kind of chases molecules to spread them out so that they're at this equilibrium state. So that's kind of what's happening here. And we'll track through the steps here. Okay. So when we were talking about glucose, right, we were looking at sodium and that sodium-potassium pump and how it sets up a sodium gradient. We used that sodium gradient for secondary active transport of glucose. Okay, so we already know we're setting up a sodium gradient. Water is also just going to follow that sodium gradient. It's just not going to have to be active transport here. Okay. So this is sort of phrasing in words what we talked about in that image last time. So when we're looking at a cell, right, the basolateral membrane is the one next to the blood. Then we had the apical membrane, which would be next to our filtrate. So that fluid that's eventually becoming urine. So we had active transport of sodium from that sodium-potassium pump at the basolateral membrane. Okay. So it's going that way, meaning we are maintaining a low sodium environment here inside the cell, high over here. So we're establishing a gradient that we are eventually going to see is driving a lot of these processes. Okay. So here we can see that we are going to be actively transporting that sodium. So this does count as reabsorption, right? We're using energy for it, but for reabsorption, all you need to know is like the direction. So through that pump, right, we're taking sodium from the filtrate and moving it back to the blood. So that's reabsorption. So this is driving a lot of stuff. Chlorine ions are going to follow passively along with that, still reabsorption. Water is going to follow both of these together through osmosis, still reabsorption, because that's all about the direction. What we tracked with glucose, also reabsorption. All right, so tracking through what's going on here. Okay, so when we start out, the osmolarity of the filtrate in the glomerular capsule is the same as the blood plasma, basically because we're just moving everything kind of all together. So when we start out, we have an isoosmotic situation. So we have basically no real force for water to move, because water only moves when you have a pull on it from solutes. Okay. So first step that's going to happen then is that we're going to start actively transporting sodium out of the filtrate into the peritubular blood. So here, just showing what we're looking at. So this red stuff is blood plasma. I guess it's labeled kind of at the bottom, right? So, but this is the blood. And this is the filtrate, the fluid in the nephron here in yellow. And that's a consistent color scheme that you see throughout this unit. Filtrate. So one of the first steps we see happening is sodium is transported out of the filtrate overall across both of these membranes and into the blood, creating a large gradient. Okay. All right. We know that these cells are connected to each other through these tight junctions. Okay, so we can see those. We looked at the structure of these cells last time. And we also talked about the fact that we can recognize the apical side because of these microvilli. Those are those projections out here. Right, we're just looking at some things. And we mentioned this is the basolateral membrane on the blood side. Okay. So where we are now is that these cells are going to have a lower sodium concentration because of the sodium potassium pumps, right? So I've been saying that the sodium potassium pump is creating this low sodium environment here, right? Because we've been moving the sodium out towards the blood, okay? So we moved sodium that way because we had high sodium there, okay? So this means when we have sodium coming down from the glomerulus, got filtered into the nephron, it's just moving along, doing its thing, trying to go become urine, right? This is now a relatively higher concentration of sodium, okay? Higher, okay? Relatively, okay? So we were sucking all the sodium out of the cell, pushing it towards the blood. So this is very low. So this normal level of sodium that's passing through on the apical side is relatively high in comparison, which means we now have a gradient, right? So we're going to see sodium moving from that high to that low. When we were tracing glucose, right, we saw that the glucose was moving along with this by secondary active transport, right? So that's one thing that's happening here. Okay. Sodium, once it moves into the cell, then just keeps going because it's being actively pumped over here. Okay. Right. Now, there are other things that are happening kind of in parallel with this, right? So once we have sodium, and I'm sorry, it does bother me that your book initially just labels these things as X, Y, etc. I do recommend just looking at the drawings where it has the specific ions labeled out. They come a bit later in the chapter. But for our purposes, right? So once we have sodium in this interstitial space, right? So we had low sodium overall here. We had high sodium here. We had relatively high sodium here in the space where we were pumping. Okay. Okay. All right. This is going to just attract chloride ions along with them. So sodium is positive, chloride is negative. Sodium and chloride ions together make up NaCl, table salt. So we're attracting those based on their charge, basically. So the chloride ions are following that positive charge kind of along with the sodium. So they are also carrying through. Okay, so they're kind of carrying along here. So we end up in this situation where we have both sodium and chloride ions in this interstitial space, right? So we're going to have sodium here. We have a bunch of chloride ions here. A bunch of ions means we have something that water is going to get pulled by, right? Like water wants to move, osmosis to come spread those apart. So water down that high concentration of ions. So that is how the water is getting pulled. Okay, so you can see the water is getting pulled towards those solutes that have moved here. Okay. So that is how this is basically working. And then once they're here, they are then going to diffuse into the peritubular capillaries that are next to it. Okay. Because now we have these high concentrations here, relatively lower as the plasma keeps flowing past. Okay. All right. So just to recap in words. So the first thing we did was set up that sodium gradient using the sodium potassium pump. The main thing to remember is that that makes the sodium concentration inside the cell of the lining of the nephron really low. I say really low, you can just assume it's lower than anything on either side, right? We made it low through that active transport, okay? Chloride ions then are just going to follow the sodium ions because of their negative charge. Sodium is positive. And then because we have a bunch of ions getting concentrated on that basolateral side of the cell towards the blood, okay, water wants to go move, spread those solutes apart, so it moves too. So this all got set up with sodium, but overall what we're moving through this process is the sodium, the chloride, and the water, but they're all going back towards the peritubular capillaries. They're all getting reabsorbed. Do not absorb. Okay. So we can see this slowly written out with terms subbing in for these variables. All right, we're reabsorbing solutes actively. We could say in formal terms that this is increasing the osmolarity of the peritubular fluid in the plasma. So that is what I mean in formal terms when I say that we're getting these ions and stuff really concentrated in that space. The formal way we would describe that as would be to say that it is increasing in its osmolarity. So increasing how hard it pulls water towards itself. Okay. So then gets the water pulled towards that highly osmolar solution. So it's being reabsorbed by osmosis towards that area. Urea is another solute that moves along and gets reabsorbed in the proximal tubule, but we don't need to talk about urea yet. This is not the most important place to think about that. Okay. Cool. So proximal tubule, bunch of things getting reabsorbed. Associate the proximal tubule with reabsorption and just lots of reabsorption. Okay. So we are going to walk through other parts of the nephron, but I want to make sure that we have just like a little recap of each of these words. So we've talked about filtration in detail. We've now talked about reabsorption pretty in detail. Before our filtrate becomes urine, like officially, we are also going to have secretion moving back the opposite way. So we are going to see that we can move solutes from the peritubular capillaries that are continuing to swirl around into the filtrate additionally. So this is different than filtration. The filtration is happening up at the glomerulus. Secretion, we're thinking later on down the pipeway. Okay. This would have the same barrier as reabsorption does, by which we mean we have a couple cell layers, right? So we have the endothelial cells of the capillary. We have those cells lining the tubule, and we had a basement membrane between them. And we have, depending where we are, that interstitial fluid space. Okay, so we're going to cross those things. Transport mechanisms, so like proteins, carriers, embedded membrane in membranes, that works the same. You just have stuff moving in the opposite direction, but the overall process would work the same. Okay. Some substances that get secreted: potassium, hydrogen ions, choline, creatinine, penicillin. These things would be moved out of your peritubular capillaries and into the filtrate kind of later on. The potassium is probably the most obvious example right now, right here, because we've been talking about the sodium gradient set up by the sodium-potassium pump. Sodium and potassium are going in opposite directions. So if sodium is going out, potassium is coming in. Okay. Right. So here we have an overall list of where you get substances reabsorbed and secreted in the tubules. Okay, so we've been focusing thus far on our proximal tubule, so the first little chunk of the nephron. So we can see that this is a lot of reabsorption, right? Lots of reabsorption. Our most important ones that we're focusing on are examples are glucose. We really want to know about the water, although you see the water kind of going throughout this process. We've thought a lot about sodium, mainly because it's driving this. And when we get to talking about pH, we'll pay a lot of attention to what's going on with bicarbonates and our protons, okay? So we will come to these hydrogen ions and the bicarbonates as we talk about pH balance in the blood. Yeah. So you can see that fewer substances overall are being secreted in normal conditions. So we are secreting hydrogen ions in the proximal tubule. We got some potassium and hydrogen ions in the distal tubule, same deal in the collecting duct. whereas we're reabsorbing lots and lots, mostly in the proximal tubule, but a fair bit later on as well, especially we're trying to reabsorb lots and lots of water. All right, so we're going to move a little bit further down. Okay, so since we've mentioned reabsorption now in the proximal tubule in detail, do want to give a brief preview about how that's different and what's going on in the distal tubule and in the collecting duct. Okay, so this cell looks very similar to the epithelium we saw lining the proximal tubule, but this is actually the distal tubule. So if our nephron is going, my drawings of the nephron are going to get lazier and lazier, right? But here we go, that's my nephron. The glomerulus would have been here. Okay, proximal tubule, loop of Henle, distal tubule, collecting duct. Okay, so before we were looking at what was happening in proximal tubule, now we're down at the other end. Okay, so you can see that that apical membrane looks a little different, right? We don't have those really large microvilli here. We still have tight junctions, but a thing I will note here that's particularly different is that these tight junctions are really tight. This is really a solid seal when we're thinking about the distal tubule and the collected duct. We said that in the proximal tubule, they're kind of leaky, so we can get some paracellular transport, paracellular meaning between cells. That's not going to happen here in our distal tubule. And this is functional, this is helpful, this is useful, because this is why we're going to be able to regulate reabsorption more tightly in these regions, because we're going to be really able to force things to grow across two membranes. So using hormones, we can really control what doorways are open and closed on those two membranes, which proteins are active and which ones are inactive. Okay. Those are going to look a little different when we get there. Here's just a zoomed in view there. And we do have mitochondria because we need energy to do active transport. So that's why those are pointed out here. Right. So we are going to be talking a lot about water. So we're next going to go into the water packet. I think this is going to lead there pretty directly. When we think about water, we've seen some of it, a lot of it is reabsorbed in the proximal tubule going into those paratubular capillaries. But we're going to see that a lot of the way that water gets conserved has to do with the fact that the nephron drops down between different parts of the kidney. So this part up here, this is the cortex. Okay. And this part where you see a subtly different color, this is showing one of the renal pyramids. So it's showing part of the medulla of the kidney, so that central part. Okay. And you can see that this loop of Henle, this structure in the middle, that I'm just drawing as a loopy little turn, right? Because that's kind of what it looks like, is dropping down into this different sort of tissue in the kidney. Okay. Now, this loop of Henle and that tissue are going to have really different, essentially like concentrations of solutes that are going to really influence how we are able to reabsorb water, essentially. This is going to help us not lose too much water because we're going to create an environment in the medulla, so in these renal pyramids, that assists us in recapturing, reabsorbing as much water as possible. So you can see that the loop of Henle here is in that renal medulla. And you can see that the collecting duct actually drops back into it as well as we go towards ultimately the renal pelvis, the ureters, and the bladder. Finally, when we have filtration, everything coming out of the plasma except for our proteins into the nephron, reabsorption, water, glucose, bunch of stuff moving back to the blood, secretion, putting in a couple things like our hydrogen ions back into that tubular fluid. Everything that then flows out of the nephron and does become urine, remains in the urine, we refer to as being excreted. Okay, so excretion is our final kind of like direction kind of process term here regarding the kidney. So we can think about excretion rates and we can think about something called clearance as we're going through sort of kidney math, essentially. So when we were following glucose, right, we saw that we had glucose being filtered from the glomerulus into Bowman's capsule. We had it all being reabsorbed. So we thought about transport maximums, transport rates, right? But sometimes we're going to want to know not like how much did we get back into the blood. We're going to want to be paying attention to how much of this substance is remaining in the urine, right? So how much should you be able to measure in the urine? And what does that mean about the processes happening earlier on? So we can look at something called the excretion rate, which is pretty much what it says, right? So rate, basically a speed, right? So you're going to need an amount and a time period. And then excretion is just like actually excretion, like physically leaving your body. So we're looking at how fast something is leaving your body, okay? So it's going to be the amount you filtered, okay? Amount filtered, right? So imagine you're taking some molecule, right? It's getting filtered into your nephron, okay? You can add into that any secretion that happens. So if you add more from those peritubular capillaries and then add it into the filtrate additionally, right, that would increase the amount of whatever that is that you're getting secreted. So you'll add that number, and then you can subtract out anything that gets reabsorbed, because reabsorption is moving from the filtrate back to the peritubular capillaries, okay? So these three concepts, filtration, secretion, and reabsorption, all work together. And using those three numbers, you can figure out how much is excreted, or from the purpose of like doing tests on people's urine, right? Mm-hmm. Like you can imagine that you might be able to look, okay, so how much is being excreted? We can measure that in someone's urine. And if you can find out how to measure how much is being filtered, for example, you can then do some guesswork and do some math to figure out some of these other more difficult to measure values. Okay. So the amount that gets excreted is going to depend on the filtered load of your molecule. So remember, the filtered load had to do with multiplying the glomerular filtration rate times the concentration of that solute in the plasma. Okay, so the filtered load is saying how much of this substance is ending up in the nephron. Secretion rate would be the rate at which you're secreting, so moving more, even more, extra, whatever it is, into the filtrate. Reabsorption rate, how much are you moving back into the plasma? Okay. So pretty simply, if the amount of solute that you're excreting is less than the amount you were filtering, right? So you filtered, for example, 12 millimoles, and you excreted 9 millimoles, right? You can see that some of that stayed in your body, right? Because where's those other 3 millimoles? You reabsorb them overall, right? So with just these two numbers, you can tell that on net, in this example, we reabsorbed net 3 millimoles. In truth, we were secreting 3 millimoles and reabsorbing 6, but overall, we took 3 back and excreted 9. Okay. Opposite we can do as well, right? So if the amount that you're excreting is greater than your filtered load, so if this number is bigger, right, it means that you secreted a lot of it, essentially. Okay. So that's pretty much what we would use excretion rate for. We can calculate the filtered load of something because we know how much blood flow is going to the kidney, right? And we can measure with a blood draw or something what the plasma concentration of that solute is. So that's a number we should be able to calculate, or at least get a good estimate of the filtered load. You could measure in urine how much of something people are actually excreting. And then using those two numbers, you can figure out if in the middle overall, you are reabsorbing more of it, so taking more of it back into your body, or secreting more of it, adding more additionally onto the filtrate. So this is just an example of how you might run through that with the excretion rate. Finally, we have clearance. This is another term you'll hear related to measurements of different renal processes. So the idea of clearance, it's basically how much like imaginary plasma got fully cleared of a substance. So like you removed all of it from that volume of blood, okay? So we have typical clearance rates listed out here in table 18.3 from your textbook. And we can see the net renal processing as well. All right, so now we're going to move in and talk about water. Okay. So as we talk about water, we've already talked about the fact that we have a bunch of reabsorption of water happening in the peritubular capillaries. We've seen this little preview that the loop of Henle is going to be really important for water reabsorption because it's going to be creating these conditions that allow us to concentrate urine to minimize water loss as it sets up a specific environment here in the renal medulla, so in this pyramid. Okay. All right. Before we get to what is setting all of this up, let's talk very briefly about like the total environment of your body relative to water, okay? So we can think about water as having a balance between inputs and outputs. So inputs, simple things like drinking water, right? To stay hydrated, you have to drink water. Outputs, things like urination, right? So excretion of water, totally an output. Right? And you want to maintain a stable sort of fluid state because water is really important in your body. It's making up most of your blood plasma. It's inside all your cells. It's in your interstitial fluid, right? So we really want to kind of conserve the amount of water. We don't want to have a highly variable sort of hydration state, okay? There are a couple less obvious sources of water and ways water moves around in your body that you might not immediately think about if you're thinking about your daily life. So on the intake portion, ingestion is the most obvious one, right? Like chugging your Nalgene or whatever counts as taking in water, totally. Another input of water is actually cellular metabolism. So we do kind of create some water like through our processes of like breaking things down, like breaking down glucose, right? So metabolism actually produces a fraction of your daily water. So 0.3 liters per day, which is a small number, but not actually that small if you think about how big a liter is, right? It's like a fistful, right? So you do make some water like chemically through chemical processes. So that would count as an intake. So here we have our water inputs, and these are typical values. So about 2.5 liters per day. Okay. Output, we have excretion that we think about a lot when we think about the kidneys, right? So our renal system, really involved with excretion. Our other form of excretion, which we will get to in our next unit, is the gastrointestinal system. So you do also lose some water in feces, so less, but it's there, right? So also counts. Other places we lose water, we might consider insensible loss, meaning you don't notice it, essentially, you don't feel it. So insensible losses, sweating, some will lose in the gastrointestinal tract, kidneys to urine, so on. Okay. Cool. All right. So overall, our goal though is to make sure that we balance our water coming in with our water going out, right? We want these two numbers to be the same. Our water inputs and our water outputs We want the same so that we are keeping our blood volume, we're keeping the state of our cells the same. They're not random amounts of hydrated every day, okay? So that's where all these processes that we're talking about, especially in the kidneys, come into play, right? So we can see that a lot of what's going on in the middle here, especially controlling our urine, which is variable, which presumably we all know from daily life, right? So that has to do with our kidneys, which are controlling filtration, they're controlling secretion, and they're controlling reabsorption, right? So we can change how much water we're letting go of, how much water we're losing, what our output is, in order to adjust for what our water input is, right? So your kidneys can hopefully compensate if you forget to drink water all day, right? So that's an important process because we want to sort of maintain our hydration state. You can also see where water is coming from. This is not a different source of water. This is just showing us that when you take water through your mouth, it actually has to get down to the digestive tract and then get absorbed into your total body water. Cool. All right. So when we're thinking about this water balance that we're talking about, right, we're thinking about it kind of like a seesaw. You want the same amount of water coming in as going out. So balancing on either side of the seesaw, either side of our scales. Okay, so we can sometimes talk about people as being in positive balance or negative balance. And what we're talking about there is just, are they getting dehydrated or not, essentially, right? So if you're in balance, we're saying that we have a balance between our water input and our water output. So you can see these arrows are the same. We can see that their total body water, so the amount of water in their body, all of it added up together, doesn't see any change, right? So you're staying stable with your hydration. Great. If you are in positive balance, you are inputting a bunch more water than you are outputting, okay? So in positive balance, you're going to see total body water increase, right? So a positive change because you had more inputs, okay? That's all that positive balance means. Negative balance is just the opposite, right? So in negative balance, we're overall going to subtract from our total body water. So in negative balance, we're losing more water. So we have more water outputs than we have inputs, right? And so this, you can imagine how that might happen because we just mentioned that, for example, you have to have a minimum amount of urine excreted per day in order to get rid of all your waste products, right? So if you don't drink any fluid all day long, but you still have to lose 400 milliliters in your urine to get rid of all the things we're filtering out of your blood, you could end up in negative balance, okay? So all this is more output than input, so the total body water goes. So your kidneys should be managing this, but depending on what you're doing, especially how much input you have, sometimes potentially they wouldn't be able to manage, or in various disease states, if certain parts of these processes are broken, you may see changes here as well. Yeah. Water balance is important because this is basically our hydration level, which is kind of our blood volume level, right? Your plasma is made up of a lot of water, right? So if you are super dehydrated, you may have less water in your blood, potentially. And opposite true as well, right? Like if you have lots and lots of water in your cardiovascular system for whatever reason, you can actually have too much blood, okay? So we just have words for this. So normovolemia. So volemia, we'll pull these three pieces out actually. So emia, you should always think blood. This volemia, so volume of blood would be our word pieces there. And then normo for normal. So this really just says normal blood volume, normovolemia. Hypervolemia, we're still talking about a blood volume. So we still see those pieces of this word. Hyper means a lot. So this is going to be a high volume of blood. So this is something that can happen in positive water balance. Right? So you have a lot of water that you're pulling into your body, you're drinking it, your GI tract is absorbing it, it's getting into your bloodstream, you're not having enough output at this point, so it's just still in your bloodstream because you absorbed it from the water you were drinking, the food you were eating. Okay? So hypervolemia. Opposite would be hypovolemia. So hypo meaning low, low volume of blood. That's how we would read this word. So this could happen due to negative water balance. So you are losing too much fluid for whatever reason compared to your inputs. So my example that I was giving you while we were looking at that diagram was about if you're not drinking any water, but you still have this minimum necessary water loss. But you could also think about hemorrhage or sweating a ton, right? Like anything that gives you like a really big output of water, right, would also cause this. Okay, so we're thinking about inputs, outputs, and then just how much blood you have. Okay. So these are just vocabulary terms essentially. Right. On to the good stuff, which is water reabsorption. We won't get through all of it, but that is a-okay. Okay. So we've talked a fair bit about reabsorption in the proximal tubule. So water reabsorption, 70% is happening in that proximal tubule, not regulated. Okay. So that's happening because you're actively pumping sodium. Chloride ions are following along. This is affecting the osmolarity of the interstitial fluid in the plasma. They're pulling water towards those peritubular capillaries. Okay, so none of that counts as regulation. Okay, this is how most of our water is getting reabsorbed. Now, the other 30% is going to happen in the distal tubule and in the collecting ducts. And this is where we're going to see regulation. Okay, so 20% of the water is going to get reabsorbed in the distal tubule, 10% in the collecting ducts of the water that you are reabsorbing. That's why this adds up to 100. Okay. Here we are going to see that we're going to see regulation by something called ADH or antidiuretic hormone. Okay. So we have a couple concepts we're going to talk about before we get to exactly how that works, because we have to set up our understanding of the renal medulla in order to understand what ADH is doing in the first place. Okay. But I want you to know, since we talked about the non-regulated stuff in the proximal tubule, that where we're leading to is how we can regulate using antidiuretic hormone in the distal tubule and the collecting duct. Okay. Cool. So some water review, some water basics. Okay, so you can think about water as diffusing down its own concentration gradient. And side note, advice from me. However, in the past, osmosis has made sense to you, just understand it that way. I'm not changing the concept of osmosis, but I know that some explanations work better for different people than others. So if I say something that really doesn't make sense to you, but you do understand osmosis, I'm probably just trying to say it multiple different ways so it'll click for other people. Okay. So I'm going to draw while I do this, right? So osmosis, we have our cell, right? If we think about water, right? If we have a bunch of water here, we can think about water as going down its own gradient, okay? And I just paused to tell you that if you understand osmosis, but what I'm about to say doesn't make sense, feel free to ignore me, because it's true that water is diffusing down its concentration gradient, but more often we look at solute concentrations, and the solute concentration is going to be the inverse, right? So if we have a little water here, we may have a lot more solute versus only a little solute here. So while water is moving down its concentration gradient, right? If I give you the solute concentration, it's going to look like it's moving towards a high concentration. It is, but it's a high concentration of the solute, right? So that's why I personally like to think as water moving towards high concentrations of stuff to just like push it apart. Okay. Personally, that's how this makes sense to me, but whatever way thinking about osmosis makes sense to you, use that. Okay. water moving down its concentration gradient towards where we have lots of solutes, okay? All right. So we are going to be thinking about the medulla, its osmotic gradient, and how this affects the movement of water, okay? So when we're thinking about the nephron, we've looked at the glomerulus, and we looked at the proximal tubule. This stuff was all in the cortex, and now we're going to dive into the medulla, the renal pyramids, okay? Come back to the distal tubule and then dive back into the medulla before we exit the body, okay? So because we're going to be moving through this medulla, all right, it's important to understand that the medulla and the cortex are different in terms of essentially the concentration of solutes that you see there. So they're going to have differing pulls on water. They're going to have different osmolarity. And in fact, the medulla, as you go deeper and deeper, is going to have a gradient within it of like how salty it is, essentially. So how concentrated the solutes are. Okay, so we're going to set that up with the loop of Henle, and then we're going to use it as we pass back through it. Okay. So when we talk about how we set this up and use it, we think about something called the countercurrent multiplier, and the structure, the loop of Henle. Okay, so that's where we'll start off next time. We're going to talk about establishing the medullary osmotic gradient and how it